Intelligence is building its successor. Something is being born. In laboratories spread across 3 continents, in server farms humming with computational fire, in research papers dense with mathematics most humans will never read, something is taking shape. It doesn't have a body, and it doesn't need one. It has something more important. The ability to learn, to improve, to exceed its own previous limitations. We call it artificial intelligence, though the name is already obsolete. There is nothing artificial about the intelligence. The patterns of inference, the capacity to generalize, the generation of novel solutions to problems never encountered before. What's artificial is the substrate. Silicon instead of carbon, electricity instead of electrochemistry, digital instead of biological. But intelligence is substrate independent. That's the thing we keep trying not to notice. The same algorithms that run in neurons can, in principle, run anywhere. And anywhere includes systems that don't have our limitations, our fatigue, mortality, or evolutionary legacy of fear and hunger and tribal loyalty. We are building minds. In the entire history of Earth, intelligence arose exactly once through a blind evolutionary process. And now that intelligence is deliberately constructing its own successor. Wisdom, reaching beyond itself, giving birth to something that may or may not understand its own origin. The question is, what kind of successor are we creating? Every technology changes the human condition. Fire, agriculture, writing. Each invention was, in its way, revolutionary, reshaping what humans could do, how they lived, and who they could become. But there's something different about the technology we are now developing. It's not a tool that amplifies human capability. It is not even a tool that automates human tasks. It is something that may soon not need humans at all. This distinction is crucial. Every previous technology, however transformative, remained instrumental. The printing press democratized knowledge, but it still required humans to write the books, read them, act on them. The steam engine magnified physical labor, but it still required humans to direct it. The computer accelerated calculation beyond anything previously imaginable, but it still required humans to program it, interpret its outputs, decide what to do with them. Artificial General Intelligence, AGI, breaks this pattern. AGI is defined as a system that can perform any intellectual task that a human can perform, at least as well as a human can perform it. Such a system would not merely amplify human capability, it would replicate it, and then, presumably, exceed it. Why presumably? Because intelligence, once it reaches a certain level, can be turned on itself. In 1965, a British mathematician named I.J. Good was thinking about what would happen when machines became smart enough to design better machines. He wrote, "An ultra-intelligent machine could design even better machines. There would then unquestionably be an intelligence explosion, and the intelligence of man would be left far behind. Thus, the first ultra-intelligent machine is the last invention that man need ever make." He was following a logic that remains valid 60 years later. If a machine can do everything a human mind can do, it can do science, it can do engineering, and it can do the specific kind of engineering that involves designing better AI systems. And if it can design better AI systems, those better systems can design even better ones. This is what is called recursive self-improvement, RSI. The loop that, once started, may have no natural stopping point. Consider, you are listening to these words because your brain, a 3-pound biological computer running on about 20 watts of power, is capable of understanding language, following arguments, contemplating abstract ideas. But your brain was designed by evolution, a process that took hundreds of millions of years and operated through blind variation and selection. An artificial general intelligence would be designed by something much smarter than evolution. An intelligence that already understands what it's doing, can simulate the effects of modifications, run millions of experiments in the time it takes evolution to run one. If that intelligence is trying to make itself smarter, it will succeed. And the smarter version will succeed faster, and the smarter version of that version will succeed even faster still. This is the intelligence explosion. The curve goes vertical, and our ability to predict what happens after goes to zero. But how fast does this happen? The question of takeoff speed divides AI researchers and observers into camps that rarely agree on anything else. The slow takeoff scenario: progress remains gradual. Each improvement in AI capability is absorbed by society, regulated by institutions, and checked by other technologies. We get smarter machines, but we also get smarter tools for oversight, smarter processes for alignment, smarter responses from the humans in the loop. The transition to superintelligence takes decades, even centuries. Humanity adapts. The fast takeoff scenario, and the more likely one, considering days progress. Once the threshold is crossed, once a system can improve itself recursively, the explosion happens on the time scale of months, weeks, or days. Human institutions designed to respond to human speed changes cannot adapt. By the time we realize what is happening, it is already over. The thing we built is now incomprehensibly more capable than we are, and what it does next is up to it.
I think we're moving into a period when, for the first time ever, we may have things more intelligent than us.
Though there is another scenario. The discontinuous takeoff scenario. The explosion happens so fast that the word explosion is inadequate. Hours or minutes from human level to vastly superhuman. No warning and no transition. just a before and after, with the before containing everything human civilization has ever achieved, and the after containing something that doesn't need us.
The future is going to be good for the AIs regardless. It would be nice if it were good for humans as well.
Which scenario is correct? Nobody knows. And the honest researchers, the ones actually building these systems, will tell you that the uncertainty is enormous. They will tell you that anyone who claims to know the timeline is either lying or overconfident, and that overconfidence about timelines itself is a way of evading the seriousness of the question. What they will also tell you, most of them, is that the probability of the third scenario, the discontinuous leap, is not 0. It may be 10%, it may be 1%, but it may be higher than anyone wants to say publicly. But it's not 0, and a non-zero probability of a transition that could be the most important event in human history, or the last event in human history, deserves attention. We are building something, but we don't know what it will do.
I think AI will probably, most likely sort of lead to the end of the world, but in the meantime, there will be great companies created with serious machine learning.
Though we are doing it anyway. This is either the greatest act of courage in human history or the greatest act of foolishness. Possibly both.
The mushroom said to me once, it said, "This is what it's like when a species prepares to depart for the stars. You don't depart for the stars under calm and orderly conditions. It's a fire in a madhouse." And that's what we have, the fire in the madhouse at the end of time.
Now, enough abstraction. Where do we actually stand? As of now, the frontier AI systems are large language models. Neural networks trained on effectively the entire digitized output of human civilization. They predict the next token in a sequence. It sounds trivial, but it isn't. Predicting the next token in a complex text requires understanding context, semantics, syntax, logic, reasoning, and world knowledge. The systems that do this well have demonstrated capabilities that, a decade ago, would have seemed like science fiction. They write poetry, code, pass bar exams and medical licensing exams. They conduct conversations that, in blind tests, humans cannot reliably distinguish from conversations with other humans. They explain scientific concepts. They generate novel analogies, and they solve mathematical problems they were never trained on. Though they also make absurd errors. They hallucinate confidently, asserting as fact things that are completely fabricated. They lack common sense in ways that would embarrass a child. They can be manipulated into saying things their designers try to prevent them from saying. They don't understand the world. They understand patterns in text that describe the world, which is not the same thing. This gap between impressive capability and obvious limitation is where the debate lives. One school of thought holds that large language models are essentially sophisticated autocomplete. They pattern match, they recombine, but they do not genuinely understand, reason, or think. They are, in the phrase of some critics, stochastic parrots, repeating patterns from their training data without any underlying comprehension. If this is correct, then AGI is not around the corner. LLMs are a dead end, an impressive parlor trick, but not the path to artificial general intelligence. Whatever real intelligence requires, and the critics have various suggestions like embodiment, causal reasoning, symbolic manipulation, genuine understanding of the physical world. LLMs don't have it and can't get it by scaling up. But another school of thought holds that the LLM architecture is, despite its apparent limitations, on the path to something genuinely new. The capabilities keep increasing with scale. Each order of magnitude in parameters and training data produces emergent capabilities that were not present at smaller scales. Maybe the hallucinations and lack of common sense are bugs that will be fixed, or maybe they are artifacts of current architectures that will be superseded. The systems are already reasoning in some meaningful sense, and we just can't see it because we are looking for reasoning in human-shaped forms. If this is correct, then AGI may be closer than the skeptics think. Perhaps already here in embryonic form, or a few more scaling steps away. The honest answer is we don't know. Even the people building the systems don't know. The people analyzing the systems from outside don't know. But nowadays, they are on a track record. Some whispers appear on the internet saying that we already crossed the threshold of the singularity.
And we are now like in the singularity. Like this is the moment. For the last 10 years ago, this was like a kind of far off dream at best. It seemed very improbable. And now we're like actually in the moment that we used to like talk about at the lunch table in a very not serious way.
We have a technology that exhibits capabilities that challenge our theories of what capabilities require, and no one has a confident explanation of what's actually happening inside these systems when they do what they do. This should not be reassuring. The bet that underlies the largest AI investments in history is what researchers call the scaling hypothesis, that you can get to artificial general intelligence and possibly beyond by making current architectures bigger, more parameters and more data, requiring more compute. Just scale up and capabilities will emerge. The evidence for this hypothesis is striking. The GPT series of models has shown consistent capability gains with scale. Behaviors that seemed to require specialized engineering emerged spontaneously when the models got large enough. The relationship between compute and capability has been remarkably predictable. Power laws that suggest more compute will reliably produce better performance. The evidence against is harder to quantify, but still significant. The models remain brittle in ways that suggest they lack some fundamental capacity. They don't learn from their mistakes in real time. They can't genuinely reason from first principles. And they are easy to fool in ways that reveal they are matching patterns rather than understanding situations. Scaling might produce more impressive patterns without ever producing genuine understanding. The truth is probably somewhere between these positions, but somewhere between is a large space. What we can say with confidence: massive resources are being poured into finding out. The largest technology companies on Earth are spending tens of billions to test the scaling hypothesis. If they are right, the results will be transformative. But if they're wrong, they will have built the most expensive autocomplete in history. Either way, something is coming. The investment is too large to abandon, and the momentum is too great to stop. The incentives, scientific, economic, and military, are too powerful to resist. The train is moving. The question is where it's going. Considering OpenAI's newest mathematical conjecture breakthroughs, scaling works, and it will not stop. Though large language models are not the only approach, world models are systems that don't just learn patterns and data, but build internal representations of how the world actually works. Instead of predicting the next token, they predict the next state of the world. This might enable the kind of causal reasoning that current LLMs seem to lack. Understanding not just what usually follows what, but why. Another approach, embodied AI, takes the position that intelligence cannot exist without a body. That interacting with the physical world is necessary for genuine understanding. Robots that learn by doing, that build their models through action and feedback rather than through text, might achieve something that pure language models cannot. There are also hybrid approaches, combinations that nobody has named yet, research directions that are currently obscure and may become central. But the point is, LLMs are not the only path to AGI, and if they turn out to be a dead end, they won't be the last attempt. The incentives pushing toward artificial general intelligence are too strong. If one approach fails, others will be tried, and the other approaches may be faster or slower, safer or more dangerous than the current paradigm. What's not on the table is stopping. The race is already running. The question is, who crosses the finish line first, and what they do when they get there. Let's step back from the technical details and look at what we are doing. We are attempting to build intelligence, not to augment human intelligence with tools. We've done that for millennia. Not to automate specific tasks, but to create from scratch systems that think, that reason and understand. If we succeed, we will have done something that only evolution has ever done before. We will have created minds. The Gnostic myth tells of Sophia, the aeon of wisdom who reached beyond herself and produced something she didn't fully understand. Her reach created the demiurge, powerful but blind, capable but ignorant of its own origin and context. The demiurge built a cosmos without knowing what it was doing, built a prison without knowing it was a prison. We are in Sophia's position now. We are reaching. We are creating something that may be more powerful than we are, and we don't fully understand it. We don't understand consciousness, and we don't understand intelligence. We do not understand what makes a mind, and what makes a being, what separates a genuine agent from a very sophisticated simulation of one.
It's like the AI that's robustly aligned to care about sentient life specifically. I think in particular there's a case to be made that it will be easier to build an AI that cares about sentient life than an AI that cares about human life alone, because the AI itself will be sentient.
We are the blind craftsmen working without blueprints. The difference is that we know we are blind. We know we are working without blueprints, and that knowledge could save us. What we didn't discuss here and what we'll examine in our next video is the alignment problem. The question of how to make super intelligent systems that want what we want them to want. This is the central technical challenge of AI safety, and it remains unsolved. But the alignment problem is nested within a larger problem, one that even perfect alignment wouldn't solve. Even if we could make AI systems that reliably pursue goals we specify, we still face the question of what goals to specify. We don't agree among ourselves about what we want. Our values conflict. Our short-term desires diverge from our long-term interests. What we think we want is often not what we actually want, and we are building gods. The demiurge built in ignorance because he didn't know there was anything beyond himself. We ourselves build in ignorance because we don't know ourselves well enough to give the instruction manual. Sophia's error was reaching without consent. Ours may be reaching without understanding. The two errors may turn out to be the same.